Stanford University.
I'm very excited to introduce to you Navdeep. Navdeep did his PhD at Toronto with Jeff Hinton, the godfather of deep learning. He's done some really exciting work on end-to-end speech recognition. His name is on most of the exciting breakthrough papers of the last couple of years when it comes to speech. So very excited to have him here. He's now at NVIDIA, and I'm guessing continuing to work on speech recognition.
Okay. Is that working? Okay. Hi, everyone. So today, I thought I'd give a high-level overview of methods that we're looking at for end-to-end speech processing. So here's the plan for the lecture today. I'll start by taking a brief look at traditional speech recognition systems. Then I'll give a little motivation and a description of what I mean by an end-to-end model. Then I'll talk about two different models for an end-to-end speech recognition systems, one by the name of Connectionist Temporal Classification, and another recent one based on listen, attend, and spell, which is a sequence-to-sequence model, something I believe you guys are familiar with at this point. Then I'll talk about some of the work we've been doing on making improved versions of these end-to-end models, and end with talking a little bit about how language models influence speech recognition, and some efforts at improving decoding, which is an important part of these models. Okay, so starting with the basic definition of what is automatic speech recognition. In the era of OK Google, I guess I don't really need to describe it, but here it goes. You have a person or an audio source saying something textual, and you have a bunch of microphones which are receiving the audio signals. And what is received at the microphone, of course, depends on how it is oriented with respect to the person. And you get these signals from the devices, one or many devices, and you pass it to an automatic speech recognition system whose job is now to infer the original source transcript that the person spoke or that the device played. So why is ASR so important? Well, firstly, it's a very natural interface for human communication. You don't need a mouse or a keyboard, so it's obviously a good way to interact with machines. You don't really need to learn any new techniques because most people have learned how to speak by a certain time. And of course, it's a very natural interface for talking with simple devices such as cars or handheld phones, or even more complicated intelligent devices such as your call center people or chatbots, and eventually our robotic overlords. So I think we need a good speech recognition system. Okay, so how is this done classically? I'll be focusing mostly on stuff we've been doing lately, which are all neural-inspired models, but I thought it would be a nice start by talking about how these things have been built classically, and see how they've been replaced with single neural nets over the time. Okay, so the classic model for speech recognition is to build something called a generative model. I don't know how many people are familiar with generative models here. Perfect. So the classic way of building a speech recognition system is just to build a generative model. You build a generative model of language. On the left, you say, you produce a certain sequence of words from language models. And then for each word, you have a pronunciation model which says, hey, this is how this particular word is spoken. Typically, it's written out as a sequence of phonemes, which are basic units of sound. But for our vocabulary, we'll just say it's a sequence of tokens, where tokens has been a class of things that has been defined by a linguistic expert. So you have the pronunciation models, which now convert the sequence of text into a sequence of pronunciation tokens. And then the models feed into an acoustic model, which basically says, how does a given token sound like? And typically, these are built using a Gaussian mixture model, or they were in the past. And these Gaussian mixture models would have very specific sort of architectures associated with them. You'd have three-state left-to-right Gaussian mixture models that would output frames of data. And these models were now used to describe the data themselves. So here the data would be X, which is a sequence of frames of audio features, X1 to XT. Typically, these features are something that signal processing experts have defined, things like features that look at frequency components of the audio waveforms that are captured, things called spectrograms and Bell filter bank spectrograms that have sort of biases very similar to human beings. So the classical pipeline proceeds as described. Now, each of these different components in this pipeline uses a different statistical model. In the past, language models were typically n-gram models. This served very well. So here, obviously, in this class, I don't really need to define language models, but you have essentially tables describing probabilities of sequences of tokens. The pronunciation models were just simple lookup tables with probabilities associated with pronunciations. Most words will have at least a couple of pronunciations, and if you have an accent, things change further. So these pronunciation tables would just be very large tables of different pronunciations. Acoustic models, as I said, would be Gaussian mixture models, and the speech processing was predefined. So the way, once you have this model built, you can do recognition by just doing inference on the data you receive. So you get some waveform, you compute the features for it, and you get X. You look into your model, and then using some fancy search procedure, you figure out, okay, what's the sequence of Ys that would give rise to this sequence of X with the highest probability. And so in a nutshell, that's basically all the way classical speech recognition systems happen. And all the magic is in how these little pieces are refined. Okay, so now welcome to the neural network invasion. Over time, people started noticing that each of these components could be done better if we used a neural network. So if you take an n-gram language model and you built a neural language model and fed that into a speech recognition system to rescore things that were produced by a first pass speech recognition system, then results are improved a lot. Also, they looked into pronunciation models and figured out, hey, how do we do pronunciations for new sequences of characters that we've never seen before? So most pronunciation tables will not cover everything that you can hear. They found that they could use a neural network and then learn to predict token sequences from character sequences, and that improved pronunciation models. So very more professional, more production-related speech recognition systems, such as the Google one, will build pronunciation models just from RNNs. Acoustic models, also the same story. People used to use Gaussian mixture models, and they found that if you could use DNN, or deep neural networks, or LSTM-based models, then you could actually get much better scores for whether frames were real or wrong. Interestingly enough, even the speech processing that was built with analytical thought process in mind about the production of speech, even those were found to be replaceable with convolutional neural networks on raw speech signals. So each of the pieces, over time, people have found that neural networks just do better. However, there's still a problem. There's neural networks in every component, but the errors in each one are different, so they may not play well together. So that's the basic motivation for trying to go to a process where you train the entire model as one big model itself. And so the stuff I'll be talking about from here is basically an attempt or different attempts to do the same thing. We call these end-to-end models because they try and encompass more and more of the pipeline that I described before. The first of these models is called Connectionist Temporal Classification and is in wide use these days in Baidu and even at Google, the production systems. However, it has a lot of it requires a lot of training, and recently the trend in the area has been to try and build an end-to-end model that does not require hand customization, and sequence-to-sequence models are very useful for that, and I'll talk about listen, attend, and spell, which is one of these models. Okay, so the basic motivation is we want to do end-to-end speech recognition. We're given some audio X. It's a sequence of frames X1 to XT. And we're also given during training the corresponding output text Y, Y1 to YL. And each of these Ys is one of whatever, 27, 28, some number of tokens, letters A, B, C, D, E, F, not sounds. We're trying to go straight towards a model that goes from audio straight to text. So we didn't want to use any predefined notions of what it means to be a different phoneme. Instead, these models will start with X, and they have a goal to try and model Y. So Y is just the transcript, and X is the audio, possibly processed with some very minimal amount of frequency-based processing. So now what we want to do is perform speech recognition by just learning a very, very powerful model, P of Y given X. So the first model that I described, the classical way of doing these things, is the one at the top. You start with Y. It's a language model. You look into pronunciation models, and you look into acoustic models, and you get some scores. These models, for end-to-end, actually just collapse them into one big model and reverse the flow of the arrows. So they're discriminative. You start with data, which is X in the features, and your goal is to directly predict the target sequences Y themselves. Obviously, this requires a very powerful very powerful probabilistic model, because you're doing a very difficult inversion task. And I'd say the only reason this is possible now is because we have these very strong probabilistic models that can do that. Okay, so the first of these models is Connectionist Temporal Classification. This is a probabilistic model P of Y given X, where again, X is a sequence of frames of data, X1, X2, XT. Y itself is the output tokens of length L, Y1 to YL. We require, because of the way the model is constructed, that T be greater than L. And this model has a very specific structure that makes it suited for speech, and I'll describe that in a second. So again, X is the spectrogram, Y is the corresponding output transcript. In this case, this is a spectrogram. Okay, so the way this model works is as follows. You get the spectrogram at the bottom, X, you feed it into a recurrent neural network. You'll notice that their arrows are pointed both directions. This is just my way of drawing out a bidirectional RNN. I'm assuming everybody knows what a bidirectional RNN is. Right, okay. So it's a bidirectional RNN. As a result, this arrow pointing at any time step depends on the entire input data. So it can compute a fairly complicated function of the entire data X. Now this model at the top has softmaxes at every time frame corresponding to the input, and the softmax is on a vocabulary which is the size of the vocabulary you're interested in. Say in this case you had lowercase letters A to Z and some punctuation symbols. So the vocabulary for Connectionist for CTC would be all that and an extra token called a blank token. And I'll get into the reason for why the blank token exists in a second. I think I forgot to point out one important thing here. Each frame of the prediction here is basically producing a log probability for a different token class at that time step. And we'll call that a score. In this case, a score Sk of t is the log prob of the probability of category k, not the letter k, but a category k at time step t, given the data x. So you'd have, let's say you took x4 here, the probability of, if you look at the softmax, let's say the first index corresponds to the probability of character A, the second symbol corresponds to the probability of character B, C, and so forth, and the last symbol in this softmax would correspond to the blank symbol itself. So when you look at this softmax at any frame, you can get a probability of the class itself. Okay, so what CTC does is, if you look at just the softmaxes that are produced by the recurrent neural network over the entire time step, you're interested in finding the probability of a transcript through these individual softmaxes over time. What it does is it says I can represent all these paths. I can take a path through the entire space of softmaxes and look at just the symbols that correspond to each of the time steps. So if you take the third symbol, that's a C in the first time step. If you take the third symbol again at the second time step, C, and then you go through a blank symbol. It's essential that every symbol go through a blank symbol. That's a constraint that the model has. And now you go through a blank symbol, and then you produce the next character, A, and then you produce A again for another frame. Then you have to produce a blank, and you can transition to a T, and then you have to produce a blank again. So when you go through these paths with the constraint that you can only transition between either the same phoneme from one step to the next one, or take from, not a phoneme, but a label, either from the same label to itself or from that label to a blank symbol, you end up with different ways of representing an output sequence. So here we had the output symbol, output sequence cat being represented in these frames as CC blank, AA blank, T blank. There's many other paths that also correspond to the character sequence cat. So for example, if you wanted to produce cat from the sequence of tokens here, you could also have produced it from the way the second line here maps it out, where you would say CC blank blank, and then produce an A, then you produce a blank, and then you produce a T, and then you produce a blank. So all this sounds complicated, but really all it is saying there's some paths you can take through this sequence of softmax, and it's got a certain constraint that you have to follow, namely you can only transition between yourself and the same symbol again, or yourself and a blank. So given these constraints, it turns out even though there's an exponential number of paths by which you can produce the same output symbol, you can actually do it correctly because there exists a dynamic programming algorithm. I'll spare you the details of that dynamic programming algorithm today, but it's not as complicated as it sounds. I'd refer you to the paper if you're interested in finding out what that is about. Anyhow, the nice thing about this model is you are able to sort of take in inputs and produce output tokens and learn this mapping because the probabilities can be computed accurately, and not only can the probabilities for an output sequence be computed accurately, you can get a gradient, which is the learning signal that you require to learn a model. And once you get the gradient from that learning signal, you can backpropagate that into a recurrent neural network and learn the parameters of the model. Feel free to ask any questions at any time. I'm happy to answer questions. Sure. Mm-hmm. So the question is, are we using process raw audio, or can we actually do raw audio? Or maybe even what do we do in practice? So we found some years ago that we could actually use raw audio. However, it didn't actually beat the best way of processing the raw audio minimally, which would be just computing a spectrogram and then adding the sort of bias that human hearing apparatus has. It turns out the human hearing apparatus doesn't have a linear resolution on frequencies. You're able to separate frequencies that are fairly close by in low ranges, and then it becomes logarithmic, and you have to be really far apart in frequency space to tell them apart. So if you impose that bias, you get a log-mel spectrogram instead of just a linear spectrogram. People have tried to improve upon the log-mel spectrogram, but the attempts have been not very good when it comes to single channel. There's the case where you might have multiple devices, where you have multiple microphones that are recording things, and there you can actually pick up subtleties, such as one microphone being closer to a person than the other, and then it turns out that you can actually use raw waveforms to produce better results than spectrograms. So I haven't talked about that much here, but what you feed in is really not that important. For sake of calling it end-to-end, let's just say it's a little convolutional model that works on frames of raw waveforms. So you just take the original raw waveform and you split it up into little frames. And that works just as well. Unfortunately, it doesn't work better yet. as we had originally hoped. It's unless you have multiple microphones, in which case it does. So here's some results for CTC, how it functions on a given audio. This audio stream corresponds to his friends. And if you look at the model I've aligned, well, listed from the paper, so we have aligned a raw waveform at the bottom and the corresponding predictions at the top. So you'll see it's producing the symbol H. At certain point, it gets a very high probability, goes straight from 0 to 1. So it's confident it's heard the sound corresponding to H. There's a faint line here which corresponds to the blank symbol. And you'll see that when you want to emit symbols, the blank symbol probability starts to dip down to 0. So they swap out in terms of probability space because you're now confident you want to produce an H symbol. Over time, you can see this H now dives down to 0. And of course, as the audio proceeds, you start getting high probabilities for the other characters corresponding to the sounds. To give you some examples on what this is, how this looks like when you just take about 81 hours of data and just train to the text corresponding to 81 hours of audio. So imagine you're a child, you're born, you listen for 10 days, and you start producing text like this. So the target is to illustrate the point, that is if you listen 8 hours a day, which most kids don't. To illustrate the point, a prominent Middle East analyst in Washington recounts a call from one campaign. To illustrate the point, a prominent Middle East analyst in Washington recounts a call from one campaign. Here's another one. I'll let you read that at yourself. I'll just point out boutique became boutique, which is kind of cute. And sometimes it gets it quite good. So, it's pretty interesting that it produces text that very much is like the output text that you desire. Of course, turns out these sound very good. If you read out the transcripts, it sounds like what you've heard. So clearly something's missing. And what's missing is correct spelling and also notion of grammar. So if you had some way of ranking these different paths that you produce from your model and re-rank them by just a language model, you should get much better. Turns out in this case, the original base model had a word error rate of 30%. That means of the words that it was producing, 30% were wrong, which seems like a very big number, but like even a small spelling mistake will cause that error. Now, if you use a language model to sort of re-rank different hypotheses, you can get that word error rate down to 8.7%, which is just using 81 hours of data. Subsequent to this work, Google looked into using CTC, where they actually have a language model as part of the model itself during training. And that's kind of the production model you use now when you call in with OK Google. And that fixed a lot of these issues. And of course, they use thousands of hours of data instead of 81 hours of data. And there's no such thing as big data or big enough. So if you look at their paper and look at some interesting results when you change the targets, so instead of using characters, you can actually use words. You can have a different vocabulary size for words and see how the recognition system performs. So here, the top panel is where there are 7,000 words in the vocabulary, and the bottom panel is where there's 90,000 words in the vocabulary. The actual text to be produced is to become a dietary nutritionist. What classes should I take for a 2-year program in a community college? If you look carefully in the panel, I'm not sure if it's entirely visible all the way back, but these things are color-coded in terms of the different words that were produced in this window, and the height corresponds to the probability. So here, there's the blank symbol, again, which goes up and down, depending on whether a symbol is being produced or not. It has this word to, which is the first word here in green, so it's got a high probability. Also note that it also is confused a little bit about the word do at the same time. So it's either to or do. Do has a much lower probability. So it produces 2, and then it produces nothing but a blank symbol, and then it gets to the next word, and it produces the word become, and then the word a shows up, and then dietary. Turns out dietary is not in the vocabulary size of 7,000, so it just produces diet, which is in the vocabulary, and you'll see this row here corresponding to diet being yellow. It also produces Terry, the name. It doesn't have dietary, but it just produces Terry as a response. It also produces military and some other targets. But overall, it gets most of the words that it's expecting correct. If you increase the vocabulary size to be large enough so that dietary is in the vocabulary, you find that it actually also produces dietary as an output in there, although it also produces diet. So a language model would fix that kind of an issue. So that's what I have to say about CTC. I'm afraid I have to switch here, and let's see. There we go. I promised to manage with 4 switches. Yeah. Okay. So now switching gears in terms of the models. The CTC model is interesting, but if you were paying attention very carefully from a modeling perspective, you'd find that the model makes predictions just based on the data. And once it's done with making those predictions for each frame, there's no way of adjusting that prediction. It has to do the best it can with those predictions. An alternative model is the sequence-to-sequence model, which you guys have been reading about from looking at your lectures. So I won't talk too much about the basics and jump straight in. We have a model here which basically does next step prediction. You're given some data x, and you've produced some symbols y1 to yi, and your model is just going to predict the probability of the next symbol of p of yi plus 1. And your goal is basically to learn a very good model for p, and if you can do that, then you have a model for p of any arbitrary y given x. So this model that does speech recognition with a sequence-to-sequence framework changes x. In translation, this would be a source language. In speech, the x itself is this huge sequence of audio that is now encoded with a recurrent neural network. What it needs to function is the ability to look at different parts in temporal space, because the input is really, really long. I think if you look at translation results, you'll find that translation gets worse as the source sentence becomes larger. This is because it's really hard for the model to look precisely at the right place. Turns out that problem is aggravated a lot more when you have audio streams. Audio streams are much longer. Typically, a frame is like, you have 100 frames per second, and when you want to transcribe something that's 10 seconds long, that's about 1,000 input time steps long, as opposed to in translation, you might have like 40 tokens, 40 token words that you're going to translate. So it's a very aggravating problem, and you need to do attention if you want to make this model work at all. Whereas with translation, you can get by without attention. So how exactly does attention work here? You're trying to produce the first character, C, and you have this way of producing an attention vector. I'll go into that shortly, how that's done, but it's fairly standard. This attention vector essentially looks at different parts of the time steps of the input. Here it's saying, I want to produce the next token, and to produce that token, I should really look at the features that were over here and the features that were over here. So once it looks at the features corresponding to those time steps, it's able to produce a character C, and then it feeds in the character C to itself and produces the next character, which is A, after changing the attention. So the attention now looks further down from where it was looking at the first time step, and then you feed in the character A into your model, and again, you recompute attention, and it automatically just moves forward once it's learned. So if you keep doing this over the entire input stream, hopefully I didn't go, then you get a moving forward attention just learned by the model itself. And so here it's producing the output sequence, cancel, cancel, cancel. The question was, are we no longer doing predict the previous token or the break? So this is a different model, which is a sequence-to-sequence model. You feed in the entire data as an input conditioning, and there's no notion of consuming a little bit of the input and then producing output. Instead, the entire input is looked at every time step, and so you don't really need to add breaks anywhere. You just produce one token, then you produce the next one, conditioned on the last token you produced. So it's going back, it's essentially doing next step prediction. So it's just doing next step prediction. In this model, you have a neural net, which is the decoder in a sequence-to-sequence model that looks at the entire input, which is the encoder. It feeds in the past symbols that you produce. Because it's a recurrent neural network, you can just keep feeding symbols and the length issue does not arise. So you fed in the past symbols as a recurrent neural network, and then you're just predicting the next token itself as the output. Okay, and I need to switch a third time. This is the second last one, I promise. So how does this attention model work? So you have, firstly, you have an encoder on the left-hand side. It seems to have a special structure. I'll go into that in a few slides. For now, just forget the fact that it has a special structure, and just remember that for every time step of the input, it's producing some vector representation which encodes the input. And that's represented as ht at time step t. So you have hidden vector ht at time step t, and you're generating the next character at every time step with a decoder. So what you do is you take the state vector of the decoder, it's the bottom layer of the recurrent neural network, that is the decoder, and you now compare this state vector against each of the hidden time steps of the encoder. And the way you do that, so semantically what that means is you kind of have this query in mind, which is this state S. And you have places ht that you're looking at as possible places where the information is present. So you take this query and you compare it to every ht. You could have done something very simple, like take a dot product, in which case the vectors would have to be the same sort of size. Or you could have done something much more sophisticated, which is you take the hidden state that you want to compare the query against, concatenate them into a vector, and then put them in a neural network, which produces a scalar value. And turns out that's what we do. So you basically have this function here, function f, which takes in a concatenation of the hidden state at a time step t with the state of the recurrent neural network, which is the decoder state, and then produces a single number, eft. Now you do that for every time step of the encoder, and so you have a trend in time in the encoder space. And that's kind of like a similarity between your query and your source from the encoder. So you get this trend EFT, and of course, these are just scalars. You want to keep these magnitudes under control, so you can pass them through a softmax, which normalizes across the time steps. And so you get something that sums to 1. And that's what's called the attention vector. The trends I was showing you was basically the trend of these attention vectors as the query changed over time. So every time step, you get an attention vector, which shows you where you look at for that time step. Then you move to the next time step, you recompute a new attention vector, and you do that over and over again. So now that you have an attention vector, what you can do is now use these probabilities over time step to blend the hidden states together and get one context value, which is this representation that is of interest to you in actually doing the prediction for that time step. So here you would take all the hidden states and the corresponding attention value and just multiply them and add them together. And that gives you a context vector, and this context vector is really the content that will guide the prediction that you make. So you take this content vector, you concatenate that with the state of your RNN, and you pass it through a neural net, and you get a prediction at that time step. And this prediction, of course, is the probability of the next token, given all the past tokens you produced and all the input that was fed into the encoder. Aha. This is exciting for me. I don't have to switch after this. Okay, so now what's this funny business with the encoder? You're used to seeing a recurrent neural network, which basically proceeds at the same time step as the input. So you get an input, you process it through some hidden states, you pass it through one recurrent step, and you move on. We found that when we did that for audio sequences that were really long, such as realistic speech in Wall Street Journal, which is one of the speech corpora, it was just not able to learn a very good attention model. Like, things just wouldn't go off the ground. And that makes sense because you have a lot of things, of time steps to look over. So typically you'll get something like 7 seconds, which would be 700 frames, and you're doing a softmax over 700 time steps. It's hard for you to sort of initially learn where to propagate the signal down to predict what the token is. So it never really catches on very fast. So this hierarchical encoder is a replacement for a recurrent neural network, so that instead of just one frame of processing at every time step, you collapse neighboring frames as you feed into the next layer. What this does is that every time step, it reduces the number of time steps that you have to process, and also makes the processing faster. So if you do this a few times, by the time you get to the top layer of the encoder, your number of time steps has been reduced significantly, and your attention model is able to work a lot better. So here's some example outputs that this model produces. I specifically want to point out that the outputs are very multimodal. And what do I mean by that? So you have an input. The truth is call AAA roadside assistance. The model produces call AAA roadside assistance as the first output. But it also produces call AAA roadside assistance. So the same audio can be used to produce very different kinds of transcripts, which is really the power of the model, and says how this model can actually learn very complex functions and actually solve this task with just one model instead of requiring many. So interestingly, if you look down, you'll see the reason why this model is able to produce call AAA and call AAA, because the training set has a lot of call XXX. And so the model learns a very specific pattern, and it's able to sort of transfer that to a different domain. Another aspect of the model is causality. And what do I mean by that? Here you have an output which is St. Mary's Animal Clinic, which is the transcript. So if you look at the attention vector over time, when you produce the first token S, it just looks at this little blob at the top. And then when you look at T, it moves forward as it produces every character. Now the model is very multimodal, so instead of just producing ST Marys, it can also produce SAINT Marys, which is a totally different transcript for the same audio. And now if you look at where the attention goes, before it would produce ST and then start moving forward when Mary came along. Here, it's the same word saint, so it actually dwells at the same time step in attention space. So that's a notion where whatever symbol you've produced really affects how the neural network behaves at the next few time steps. And that's really a very strong characteristic of this model. Okay, the question is the fact that the model produces two different transcripts a result of the fact that there's ambiguity in the pronunciation model itself? So I think that is essentially what the model tries to capture. The fact that the same word can be pronounced multiple ways, or that the same word can be, same pronunciation can be written out multiple ways, are sort of two different but related problems. One is different pronunciation producing the same token, another which does not require multimodality in a model, as long as one source of sound only produces the same token. What's happening here is more interesting in that the same sound can be written out in multiple ways. During training, clearly, it must have heard both sides. Like it's heard Saint written out as ST, and then another time it must have heard Saint written out as an SAINT. So you need it in the training data, but what's nice is that the model's really powerful enough to realize that the same sound can actually do this, and it can actually produce very different transcripts. So when we did this about 1.5 years ago, these are old results. Things are more exciting now. We found that our model was, when you didn't use a language model, it produced a word error rate of around 14%, whereas the best system that we had in Google at that time was 8. At this point, I would say I was an intern at Google many years ago, and then the word error rate was 16%, and that was the result of 45 years of work where people had customized all the speech recognition components very carefully for all these years. And this model, by just one single model that just goes straight from audio to text, gets a lower word error rate than what we were getting in 2011. So that's, I think, something to write home about, which is pretty exciting. Turns out it still benefits from having a language model. So if you feed in a language model, the 14% word error rate comes down to 10.3. So obviously, there's no substitute for billions and billions of written text sentences in trying to disambiguate speech recognition better. But just the basic model by itself does very well. So now, what are the limitations of this model? One of the big limitations preventing its use in an online system is that, if you notice, the output is produced conditioned on the entire input. So you get this next step prediction of xt plus 1 given all the input x and all the, yt plus 1 given all the input x and all the tokens you've produced so far, which is y1 to yt. So it's really just doing next step prediction, but the next step prediction is conditioned on the entire input. So if you were going to try and put it in a real speech recognition system, you'd have to first wait for the entire audio to be received before you can start outputting the symbol. Because by definition, the mathematical model is the next token and is conditioned on the entire input and the past tokens. Another problem is that the attention model itself is a computational bottleneck. For every time step, you have to look at the entire input sequence. So there's this comparison as long as the length of the input, which makes it a lot slower and harder to learn as well. Further, as the input proceeds and becomes longer, the word error rate goes down. This is really an old slide. This doesn't happen much anymore, but I'll talk about the methods we came up with to prevent this a little later. So I'm going to now switch gears to another model, which is called the online sequence-to-sequence model. This model was designed to try and overcome the limitations of sequence-to-sequence models, where we don't want to wait till the entire input has arrived before we start producing the output. And also, we want to try and avoid attention model itself over the entire sequence, because that seems to be an overkill as well. So you want to produce outputs as inputs arrive, and it has to solve this problem, which is, am I ready to produce an output now that I've received this much input? So the model has changed a little bit. Not only does it have to produce a symbol, it has to know when it has enough information to produce the next symbol. So this model is called the Neural Transducer, and in essence, it's a very simple idea. You take the input as it comes in, and every so often, at regular intervals, you run a sequence-to-sequence model on what you've received in the last block. And so you have this situation here where you basically have the encoder, and now instead of the encoder attention looking at the entire input. It just looks at this little block, and this decoder, which we call the transducer here, will now produce the output symbols. Now, notice that since we've blocked up the inputs, we have the situation where you may have received some input, but you can't produce an output. And so now we're sort of need this blank symbol back again in this model, because it really can be the situation where you got a long pause, you haven't heard any words, so you really shouldn't be producing any symbols. So we reintroduce this symbol called the end of block symbol here in this model to sort of encapsulate the situation that you shouldn't be producing any outputs. One nice thing about this model now is that it maintains causality. So if you remember the CTC model, it also had this notion of not producing any outputs, but when you produced these symbols, you did not feed back what you had produced in the past. And so it didn't have these notions where the same input can produce multiple outputs, and it didn't have the notion of causality where depending on what you've produced so far, you would really just change the computation thereon. So here, in the neural transducer, it preserves this advantage of a sequence-to-sequence model. And it also, of course, now introduces an alignment problem, just like these slides have an alignment problem too. So in essence, what you want to know is you have to produce some symbols as outputs, but you don't know which chunk should these symbols be aligned to, and you have to solve that problem during learning. I won't describe this very carefully, but I'll make a go of it. You have some output symbols Y1 to S that have to be produced, and now if you have an input that is B blocks, you can now output these S symbols along with B end of block markers anywhere to describe the actual alignment in the way the symbols are produced. And of course, there's a combinatorial number of ways in which you can align the original input to the actual block symbols. So the probability distribution turns out to be the probability of Y1 to YS given X is modeled as the sum over all the different ways in which you can produce this, you can align Y1 to S to the original B blocks. And the extra B in length comes from the fact that there's B blocks, and hence each block ends with an end of block symbol. So now it's similar to CTC. You have some output sequence, and you're going to produce them from a bunch of different ways. And all of those ways have some probability, and you have to learn in spite of that model. Unlike CTC, of course, this model is not independent at every time step. Once you make the predictions, you feed back your previous tokens. That changes the entire probability distribution at the next time step. What this means is that there's no decomposition between different parts of the input given the data. So you can't really do a dynamic programming algorithm that just simplifies this computation. So we came up with a simple way of doing this approximation of the sum, which was, let's just find the best possible alignment given your current model. So you basically try and do some kind of a beam search, and you find the best path as the output, and then you use that during training. Okay, so sorry, one more point that I should make. That's the same process you use during inference. The model itself is, you want to produce these symbols Y1 to YS. You can do it in a variety of ways. During inference, you find the best one, and you go with that one as being the actual transcript. During learning, if you take a gradient of that combinatorial sum, it comes down to this particular form, which boils down to saying, give me a sample from all the probability of aligning the outputs given the input, and then I will train the log probability of that sample. If that sounds like Greek, I wouldn't worry too much about it, but I'll say it one more time. It's basically, this happens in cases where models are a sum of a combinatorial number of terms. If you want to optimize such a model, you basically have to take the gradient of the log prob, and the gradient of the log prob turns out to be a sum of the log probs over the posteriors of the samples. And that's the case in this model as well. Of course, this is really hard to optimize, and so we replaced this entire really complicated procedure for optimization by, given an output symbol, find the best alignment and just make that alignment better. So it's kind of like a Viterbi sort of trick. So I'm just going to skip this part. Okay, the finding of the best path is kind of interesting. So I'll cover this part. Turns out if you want to find the best path, there's also a combinatorial number of ways. And so what you can do is kind of do a beam search where you keep a bunch of candidates around and then you extend them. And as you extend them, you now re-rank them and throw away the best one. However, it turns out if you do beam search, it doesn't really work. And so what we discovered was a dynamic programming, which is approximate, that works very well. And the way this works is you consider the best candidates that are produced by, at the end of a block, from producing either J-1 tokens, or J-2 tokens, J-1 tokens, or J tokens at the end of block B-1. So you know that if I wanted to produce J-2 tokens at the end of the previous block, what's the best probability? And now that corresponds to this dot here. So from that dot, you can now extend either by one symbol, or by two symbols, or by three symbols. And you get different paths that reach the source. And so now when you're considering the different ways of entering a source, you just find the best one and you keep that around. And you then now extend those ones in the next time step. It's kind of an approximate procedure because this ability to extend a symbol is not Markovian. And so if we take this max as a max of the previous step extended by one, that may be wrong because the correct path may be 2 steps away, and that would have been better. However, it seems to work very well to find an alignment that trains the online sequence-to-sequence model properly. So some results on this model. If you change the window size, that's how the block is constructed. You find that using different block sizes when there's an attention model makes the model work very well. So in these blocks, we can have attention instead of just running a sequence-to-sequence. So it's not affected by the window size of the blocks. And those are these lines at the bottom. It also turns out that you don't really need attention if the window size is small, which sidesteps this problem of doing an attention over the entire input sequence. And that's what we're really trying to get at, is to try and build a model that could do sequence-to-sequence output symbols when it needs to, but really not have to do all this computation with respect to the length. So that was basically the online sequence-to-sequence model. I want to touch a little bit about how you can make the sequence-to-sequence models better themselves. One of the things that people are doing these days, borrowing from vision, is to use convolutional neural networks. So in vision-related tasks, convolutional neural networks have been very powerful. Some of the best models for object detection and object recognition use convolutional models. They're also very effective in speech. So we tried to do this architecture in speech for the encoder side of things. So you take the traditional model for the pyramid, and instead of doing the pyramid by just stacking 2 things together, you can actually put a fancy architecture when you do the stacking. So don't just stack 2 time steps and feed it to the next layer, but instead stack them as feature maps and put a convolutional neural network on top. I think you guys have not been exposed to convolutional neural networks yet, but let's just say it's a very specific kind of model that looks at some subset of the input instead of the entire input. And so the subset that it looks at has to be matched to the structure. So if you are in a task such as vision, an image patch is a natural structure or substructure to look at instead of the entire image. For speech, also, if you look at the frequency bands and the time steps of the features, that corresponds to a natural substructure to look at. So a convolutional model will just look at the substructure. So what we did in this work was to say, okay, now we're going to change this computation, which is a pyramid, and add a lot of depth to it by adding these convolutional architectures in every step. So in the past, it was just a simple linear projection of 2 time steps together. but now it's a very deep convolutional model, which of course for deep learning experts is great because we believe the deeper the number of nonlinearities, the better it is. And this model actually adds a lot of depth that way. When we did that, we found very good results. If you take a baseline on a task called Wall Street Journal, it goes from something like 14.76 word error rate down to 10.5 just by using this very specific trick on how to do these convolutions. So deeper continues to be a good motto. Okay, now switching to what is the output space that's a very appropriate one for speech. So in translation, what happens is there's multiple ways people have discovered on how to encode the output sequence. You might produce character sequences, you might produce words and character sequences, or you might produce a subset of characters and use that as the output vocabulary. In speech, that seems not natural because what you want to do is you want to produce output tokens that corresponds to some notion of the sound that was being produced in the input. So what you would like to do is change the vocabulary so it's not just characters, but maybe bigrams or trigrams of characters that corresponds to some audio token. Basically these are, I guess this slide is talking about the different ways to do it. As I said, you can either represent the word or the characters or the words and characters. But for speech, you want to use n-grams. However, there's a problem here. Should we decide the n-grams beforehand and then just use those during training? That kind of defies the end-to-end model where we want to actually learn the entire process as one big model. So we decided, okay, what we could do is build this vocabulary, which is unigrams, bigrams, trigrams, and like whatever number of n-grams of characters, and put them in a softmax. And now the problem arises, if you have a word like hello, it can be decomposed in multiple ways. It might spell as H-E-L-L-O, or it might spell as H-E-L-L-O if H-E happens to be in the target set that you've chosen. So it's really an undefined problem, or it's a problem where now you have to deal with multiple ways of outputting the same sequence. So how should we make this choice? One way of making this choice is you get a word such as cat sits. You could just look in your token space. If you have CA in your tokens, you just say, I'm going to choose CA as the input. Then you do T, and then SI, and then T and S. So this is just very greedy in terms of how you produce the tokens. Another way is to look at the compression, the sequence of tokens that have the highest probability. Here it's basically about reuse. It's like encoding, and you would just sort of use a minimum description line. So AT happens to be a lot more frequent than CA, so you would rather choose AT as a token in this case, and the decomposition for cat sits would be C, AT, SI, and TS. That would be another way. Of course, you know, it's not clear for the audio which is the best way. So our approach was to try and learn this automatically. So you have some output Y star, which is the correct output sequence, and you try out all the possible decompositions of the same output. So you basically look at all possible ways of producing the token, and when you do the learning, you take the gradient of all possible ways of producing the output sequence and propagate that error signal down. Just to know, when does the class end? If you look at how this model performs, turns out it helps to use larger n-gram pieces. So if you take a character-based model, which was just CTC with no language model, it had 27% word error rate. If you take the sequence-to-sequence model, the last model with character outputs, it produces 14.7 word error rate. If you use a 2-gram, it does better. With a 3-gram, it does even better. The 4-gram does better on training, but worse generalization, presumably because our data set was really limited. It's just 81 hours of data, and once you start using larger and larger tokens, you can imagine it doesn't have enough evidence for a lot of the longer tokens. Similarly for 5 grams. To show you an example, the actual test is Shamrock's pre-tax profit from the sale was $125 million, a spokeswoman said. The character model produces Shamrock as CHAMROCK. The foreground model will take the sh sound straight up as SH, which is nice, and then does a lot of these things with single characters. But you can see common and bigrams and trigrams being used as a result of this. If you look at whether or not the model is actually using it, numerically, you find out that if you had trained the model by just one kind of algorithm where you just took the maximum extension, it used the n-grams more because it was trained to use these longer n-grams. However, if you look at the results that come out where you actually learn to use the n-grams, it still does a better job, does a good job of learning the n-grams, and it gets a lower word error rate. So that's quite promising in terms of achieving what we wanted to do. So now I'm switching gears here and going into some of the final shortcomings of sequence-to-sequence models when they're applied to speech recognition. If you look at the transcripts that are produced in terms of the probabilities of every token, you find an interesting pattern. Here at the top is the actual sequence. So South Africa, the solution by Francis Kendall, and actually Leon Low, it's actually, this is not the right solution. This is the highest probability one. Below each token, you have the alternate tokens that had a specific, that had a probability which was some threshold lower than the probability of the best token. So if there's no tokens below a token, that means there's no ambiguity. It's really sure that that's the token that got the right answer. If there's many, that means it's a little confused at this part of the token when it's producing the next token. So you find a very interesting trend that there's a lot of ambiguity at the start, at the first characters, but as soon as you've produced the first few characters, there's very little ambiguity as to what the next characters are, unless it's things like names. So Francis here, there's some confusion on how to sound it out, and Kendall has some probability issues as well. So this might seem surprising, but it's natural. If you're doing language modeling on a character level, once you have the first few characters of a word, you pretty much know what the word is. And so what you really want to do is produce these, be much more discriminative at the starts of words instead of, because that's where you'll make an error. If you make an error at the start of a word, you're never going to recover from it. And so if we want to fix this problem, we need to sort of address this issue. The repercussions of this problem is that if you're overconfident about the wrong word, not even a language model can help you, because you've basically decided early on what the word is going to be, and you need very precise language model probabilities to kind of get you out of the rut. So we found that there's this little technique called entropy regularization, which prevents your softmax from ever being too confident, that really just solves this problem. So every time you predict the next character, you make sure you're not becoming probability of 1 for one symbol. Instead, you say, if you're getting too confident and penalize it, that you're forced to spread the probability distribution to the other characters. Once you do that, this problem really just goes away. The baseline model that we had just improved massively. So if you remember, we had CTC on an end-to-end task for Wall Street Journal, which had some error like 27.3. Then we had there's a baseline sequence-to-sequence model that wasn't ours, but a Joshua Benjia's group that had an 18.6 word error rate. Our baseline, for some reason, was 12.9 word error rate. And then once we applied this technique of entropy regularization, that error rate went down to 10.5. There's different ways by which you can do this regularization. One is you just do entropy. Another is you say the probability distribution must look like the unigram probability distributions of the output tokens, and that seems to work better than just doing fully entropy regularization. So that's one problem. Another big problem that arises during decoding is this lack of generative penalty. I think there was a slide in your translation lecture which talked about this in a different setting, but I'll talk about it in the context of audio. When you have a very long input sequence and you're decoding it one character at a time, what you're doing is you're comparing your hypotheses against all alternative hypotheses. So every time you produce a new token, you pay a cost for that extra token. If your input's very long, then you're going to obviously, associated with the long input, have to produce a lot of tokens because probably the transcript that you're producing is very long. So let's say you have to produce 100 transcripts and you're paying an average cost of 1. That means you're going to pay a cost of 100 for even a correct transcript. Now, in your beam search, you'll probably get some examples which say the end of token symbol has a probability less than -100. I think this is a very subtle point, but the upshot of it is your model thinks it's okay to terminate an output without even looking at the rest of the input when it's not. And the reason this happens is the model has no notion of explaining the entire input. And because it doesn't have to explain the entire input, it just terminates early, and very often you'll produce very short output sequences when you should be producing very large output sequences. So to give an example, if the output transcript is Chase is Nigeria's registrar and the society is an independent organization hired to count votes, if you look at the language model cost, it's -108. If you look at the model cost, this is just the model from the last model, it's -34. And you look at the other alternatives, you get Chase's Nigeria's registrar, which has a low cost of -31. So it's just happy to just produce a short token instead of this really long one. If you look at Chase's Nigeria's, Chase's nature is register, that also has a small probability. In fact, the best probability is just to produce nothing, which is -12.5. So this is kind of an issue where discriminative models don't explain the entire data, and so they can make such errors. What we found that worked quite simply was train as usual, but during test time, add a little penalty which says, I'm going to try and make sure the sum of probabilities over a given output time step is greater than a threshold. So look at all the frames of the input. Has someone looked at them or not? If there's enough frames that nobody's looked at them, or at least with some threshold tau, then you pay a cost for that. And when you do that, all these other hypotheses that terminate early are now paying a lot of cost for every frame that they did not explain. And so they fall down and are re-ranked out. So when you do this little trick, our model now really performs quite well. This model for sequence to sequence is now able to get 6.7 word error rate on Wall Street Journal, which is the lowest for end-to-end models, including CTC with a language model. So it's very, very promising in that these sequence to sequence models can achieve such low numbers with such low amounts of data. I should point out that this really is changing the model. You train a model with one objective, but during test time, you really fiddled with the loss that you claimed was the best one. So technically, there's something wrong with the model that, that needs fixing. So finally, something very relevant to an NLP class is, what do you do about language models here? No matter how much audio you have, you'll always have more text. And that text can be really useful in correcting up errors that this model will have. So I could train on 2,000 hours of data, but that would just be about 3 million small utterances. And the language model you learn from that is not going to be very powerful. So the speech recognizer is going to make a mistake no matter what. Since I'm at NVIDIA now, I cannot take claim for that not working. So the question arises, how can we do better language model blending in these models? Because they're really end-to-end models, and you just are basically training the entire task. You're doing an acoustic model, you're doing a language model, all in one model, and now suddenly you're saying, hey, can I can I please revert back and find ways to add my language model in here? Well, one obvious way is to add log probabilities every time you do a next step prediction. You make a prediction for the next time step, and then you blend in a language model prediction with it, and then hopefully that fixes a lot of the errors. There's some cool work from Yoshua Bengio's group, which tries a bunch of other tricks to do this, which they call shallow and deep fusion models. And it's basically an extension of the simple idea that I just described, but it kind of does a little bit more in how the blending is done. Instead of just blending the actual feature, the actual log probes, it uses a model that does a linear projection, and it learns that together. I think fundamentally this is an interesting approach where you basically have two streams of predictions and you combine them. However, one of the things that's lacking about this model is that the model, in this case it's for translation, the translation model predictions don't actually affect the internals of the language model and vice versa. What you would like to do is sort of have a model that where deep fusion actually means changing of all the features that are computed rather than just summing the logits. But it's a pretty good start. I apologize. I forgot what this slide was. So when you're producing very long sequences with next step prediction, what it's doing is just looking at the next token. And I highlighted why that can be a problem. For example, when you're producing words, if you produce 3 characters, the next one is almost necessarily just decided right away. So when you have a loss function that's just looking at the next step, it doesn't have a very long horizon. When it makes a mistake here, it might just go into a wrong path that it can never correct out of. So people have been looking at how to fix this problem. One of the ways is schedule sampling, and I think you guys have looked at this, or at least talked about this in the last lecture. But what it does is, instead of taking the model and feeding in the ground truth at every time step, you feed in the predictions of the model itself, or you sample from the model. So what you're learning is, during test time, I'm going to screw up and feed in something wrong. At training time, let me do the same so that I'm resilient to that kind of mistake. What that does is it's actually changing your model so it respects long-range structure much better. There are other methods also which would be based on reinforcement learning that optimize the word error rate directly. I won't talk about this at all, but other than to say that it's another way of letting your model roll forward and generate a bunch of different candidates and then compute an error based on the candidates that you've computed. A very cool paper is this one called Sequence to Sequence as beam search optimization, and this kind of also runs your model forward, but with some interesting tricks where it runs the model forward until you've made some mistakes, and then it stops and does it again. So finally, what can we do with this model that we couldn't have done before? There are some things that you can do, one of which is multi-speaker, multi-channel setup that people don't really do yet. So flashback to some years ago, the motivating problem for speech recognition was this thing called the cocktail party problem. You wanted to be in a room, walking around, listening to a bunch of things happening, and get your recognizer to produce all the entire output. Somewhere along the way, people forgot about that particular problem, and they've been focused on just single microphone setups where you're stationary with respect to another speaker, and you kind of produce only one output as a transcript. I'd say the reason this happened is because you have a generative model traditionally, which has some transcripts in mind, and then it generatively describes the data. And that's not very natural way to sort of do the inverse problem where you can mix in a bunch of people in many different ways. The inverse problem is just track one particular individual. And that's much easier to do than try and sort of invert a generative model where you have a bunch of sources. So a model such as this, such a sequence-to-sequence model, should work very well in trying to do multi-speaker, multi-channel setup. And then there's this really cool paper that came out recently which talks about direct translation and transcription at the same time. So it takes in audio in French, and it produces English text as an output with just one sequence-to-sequence model, which just blends the last model and a translation model together, which is quite exciting. If you look at their paper, it's got this really exciting attention plot. So if you take the neural machine translation attention model, they're translating how much is the breakfast to combien coûte le petit déjeuner, or whatever. In French, it's how much does it cost, how much does the little breakfast cost, whatever. If you look at the attention model, it's looking at the right words, how it pairs with combien, which means how in French, and much pairs with the two of them as well. If you look at the corresponding attention model from the waveform and the text, it also focuses on the same sort of parts, even though it was trained in a different way with a different modality as input. So it's really cool that it's able to learn to focus on the audio, even though it's translating at the same time. And so I'd like to end here, do some acknowledgments. Most of this work was done at Brain, at least the ones that I was involved in, and have had the luck to work with some phenomenal interns. Google Brain gets a very fantastic bunch of students going by, and I've been lucky to work with them. And the Google Brain team is a phenomenal place to work at, and so I want to thank them. Cool.